All right, let's get right into it. So, you've got your machine learning algorithm all set up. You're feeding it a massive data set, maybe millions of examples, and you kick off the training using stochastic gradient descent. But how can you be sure it's actually working? Is your model getting smarter with each example, or is it just spinning its wheels?
That's the question, isn't it? When you're dealing with a dataset so big you can't possibly look at it all at once, you absolutely need a way to check your model's pulse. And in this explainer, we're going to break down exactly how you can do that and do it efficiently.
So before we get to the really clever solution, we need to understand why there's a problem in the first place. See, there's a traditional way of checking if a model is converging, but when you scale up to big data, that method completely breaks down.
And here's the core of the issue. With old-school batch gradient descent, after every single learning step, you'd calculate your error by looking at the entire training set. It's very thorough, sure, but just imagine doing that with millions of data points. SGD, on the other hand, is all about speed. It learns and updates after seeing just one single example at a time.
And this really shows you the bottleneck. You see that big sigma symbol in the formula? That just means add everything up. So if your M, your data size is, say, 300 million, you'd have to do 300 million calculations just to get one single data point on your progress chart. That's not just slow, it completely defeats the whole purpose of using a nimble, fast algorithm like SGD.
And that really is the bottom line. The whole reason we use SGD is to make progress without having to scan the whole data set over and over. Pausing your super fast algorithm to do this huge, slow, heavyweight calculation, it's like putting a giant speed bump in the middle of a Formula One racetrack. It just makes no sense.
Okay, so if the old way is a total non-starter, what do we do? Well, luckily, there's a much more elegant and way more efficient trick we can use to get that vital feedback without grinding our training to a halt.
The process is actually pretty clever and simple. As your algorithm is chugging along, right before it updates its parameters based on a new example, you just ask it one quick question. Hey, how much error did you have on just this one example? You calculate the cost for that single instance. Then you just keep a running tally, and every 1,000 examples or so, you average out the costs of that last batch and plot that one average number.
Now, the crucial thing to understand here is that this is not the true, perfectly accurate cost function. It's a proxy. It's a running estimate, but it's an incredibly useful and computationally cheap estimate that gives you a fantastic sense of which direction your model is heading.
All right, now for the fun part. We know how to generate these progress plots, but what do they actually tell us? Learning to read these charts is kind of like getting a real-time EKG for your model's health. You can see exactly what's going on under the hood.
So, let's start with the best-case scenario. When everything is going perfectly, what does a healthy, happy learning algorithm look like on our chart?
And this is it. This is the beautiful sight we're all hoping for. The cost goes down, 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 and then it starts to level off and plateau. Now, it's going to be a bit noisy and bumpy, that's just the nature of SGD, but the overall trend is a nice, steady descent followed by a flat line. This is the classic sign that your algorithm has learned what it can and has converged.
But what about all that noise? I mean, that first plot is pretty jagged, right? Well, take a look at this comparison. On the left, we're averaging over just 1,000 examples. On the right, we're averaging over 5,000. See how much smoother that trend line is? So there's your trade-off. Average over more examples and you get a clearer signal, but you have to wait longer between updates.
Okay, now let's look at a really common and sometimes misleading scenario. You're looking at your plot, and it just seems to be going absolutely nowhere.
At first glance, this plot looks pretty bad. It's just a noisy, flat-looking line. And you might be tempted to just kill the training run right there, thinking nothing's happening. But hold on. The actual story, a very slow but steady downward trend, might just be buried under all that noise. So before you give up, the first thing to try is just increasing your averaging window. Go from 1,000 to 5,000 and see if a clearer pattern emerges.
Now for the big one. The one signal that means you need to hit the brakes immediately. There's one clear sign that things are going seriously wrong.
And there it is. That's the alarm bell. If your cost is consistently going up, that means your model isn't just failing to learn, it's actively getting dumber. This is called divergence, and pretty much every time you see this, it means your learning rate, or alpha, is just too high. The steps it's taking are too big. The fix? Stop everything, restart the training with a smaller alpha.
This actually leads us perfectly into a deeper dive on the learning rate itself. It's just this one little number, but it has a huge impact on not just if your model learns, but how it ultimately finds a solution.
This contour plot is a great way to visualize what's happening. Think of the bullseye in the middle as the perfect answer, the point of minimum cost. With a constant learning rate, SGD gets really close to that center. But because it's always taking steps of the same size, it can never perfectly land on it. Instead, it just sort of oscillates and wanders around that optimal point forever.
So how do we stop the wandering? Well, we can tell the algorithm to take smaller steps as it gets closer to the destination. And that's the whole idea behind a decreasing learning rate. You use a formula like this one, so that as the algorithm runs longer and the iteration number goes up, the learning rate alpha gets smaller. This shrinks those oscillations, allowing it to settle down much closer to the true minimum.
So which one should you actually use? Well, honestly, there's a trade-off. Using a constant alpha is way simpler, and for most real-world applications, it gets you close enough. It's the standard approach for a reason. Decreasing alpha can squeeze out that little extra bit of performance, but now you have two new parameters, two new constants that you have to spend time tuning.
Okay, so let's wrap this all up. The big takeaway here is that you do not need to fly blind when monitoring SGD. You don't have to do those huge, expensive scans of your data. The trick is to just take these frequent little pulse checks by averaging the cost over a small, recent batch of examples. These plots become your dashboard. They're the tool you use to diagnose what's happening, and then based on what they tell you, you can make the right tweak, which is usually just adjusting that learning rate.
And that's really the power of this technique. It takes you from blindly hoping your model is working to actively observing and guiding the process. It gives you a window into what was once a black box. So the only question left is, now that you know how to look, what are you going to find?